So far we've talked about some of the major types of biomolecules. Last week we did carbohydrates first, we did nucleic acids, and we've done lipids. The last one that we have to talk about is the most important, and it is enzymes. So in your notes, you want to label these enzymes, maybe label it number 4, the last and most important type of biomolecule, and that will be our topic for today. This will likely take most of today and then probably part of tomorrow as well. So if you don't finish this video today, you'll resume it tomorrow. In addition, if I go too fast, you know the drill. Either bang your head on the desk, or probably the better solution would be raising your hand and let Miss Calloway know that I'm going too fast, and she can stop the video or pause it so that you can finish writing anything on the slide. So if it goes too fast, just raise your hand, let someone know, and we can all pause and make sure you get everything. Remember, you don't have to write everything on every slide, but you want to get the major information, specifically things about structure and function. So I'm going to remove this beautiful picture of myself, so take a minute, drink it in, and here we go. Alright, so the first thing we're going to go through here is what an enzyme actually is. And the most important thing you need to recognize in terms of enzymes is that they are mostly proteins. With proteins, we're going to talk about 2 major kinds, the first one being tertiary, the second one being a quaternary structure. If you think back to ecology, we talked about tertiary being that kind of top predator, the 3rd level. Quaternary, if you're not familiar with that word, think about it in terms of money. You have a dollar, which is made up of 4 quarters, and so quart, Q-U-A-T-E-R, usually is going to be reminiscent of 4. Tertiary would be 3. So with proteins, you're going to start with long chains, and then they'll be kind of folded up a little bit. And then when we get into our tertiary and quaternary structures, they'll start to just kind of look like this. So when you draw a protein, you can basically just draw a big squiggle and then label it protein. And everyone will think you're very smart. The second thing is that proteins and enzymes work as catalysts. Catalyst is a new word here, and what it means is that it is going to accelerate the reaction that's taking place. A lot of things in your body require enzymes and require proteins in order to speed them up so that they can happen fast enough for the body's needs. So being a catalyst is an incredibly important thing and something we're going to talk about in these notes a lot. Lastly, it's important to note that they are not permanently changed in the process. Your body is making proteins, but in terms of catalyst, the catalyst itself is oftentimes used in many reactions before it has to be replaced. So here we have an image. This would be showing you a protein. Some of the most complicated things that the body can make, but some of the most important. We'll talk later on as we go through these notes about the difference between this strange kind of opening, the shape on the right-hand side, versus the rest of the protein itself, but I don't want to get ahead of us. Alright, continuing. When we talk about catalysts and enzymes functioning as a catalyst, the thing is enzymes usually only do one job really well, so they are specific for what they will catalyze. As we said, they're not going to be consumed in the process, so they are reusable. Oftentimes they will end with the suffix ase. That is really important. So for example, instead of sucrose, remember we had a sugar, sucrose. We had things like glucose. Remember, if it ended in ose or rhymed with gross, we usually called it a carbohydrate. Here, if it ends in ase, we know that it's an enzyme. Sucrase, as you might have guessed, is going to help us break down sucrose. We have lactase, this would be another example. Maltase, if you remember our disaccharide, maltose. And then here we have an image. Now, on this, there's 2 new words, and I actually want you to write these words in your notes there. We have something called the substrate, and we have what's called the active site. The active site is when we're going to have something coming in, and we're going to have the substrate, in this case, binding to the active site and allowing our enzyme to actually start working. So if this was an example being sucrase, maybe we have some substrate here and that triggers our enzyme to start catalyzing and doing some reaction. Okay, So when we think about enzymes working, we mentioned how they help us run reactions. The way they actually do that is when the enzyme is present in whatever reaction is taking place, what's actually happening is it's weakening the bonds. It's making it where it's easier for us to break those chemical bonds and release energy. So in the presence of an enzyme, you need to write this for sure, very important, we're actually going to lower the activation energy. If you think about that word activation, that's like the amount of energy required for us to start the process. So if you notice on our graph here, and you might even sketch this kind of easily in your notes, draw a little curve, a little bit of a hill, and then it starts to go down towards our product. That activation energy, activation energy is this little hill that we have to overcome. When we see that the enzyme is not present, our molecule might have to go all the way up here in order for the reaction to actually run, for us to go from reactant, the thing that is trying to react, to our product, the thing we're producing. So when the enzyme is present, notice what happens. It says the enzyme lowers the activation energy, going from the previous hill to now kind of a nice little flattened area, so that instead the reaction is just going to kind of go straight down. And it's much easier to go down that than it is to climb and then fall down. And remember, this is showing you energy on the y-axis. So the less energy required to make the reaction work, the easier it is for our body to run that reaction, whatever it may be. So when you notice the difference between the top hill and the lower hill being right here, that's what we're talking about with weakening bonds and lowering activation energy. And remember, if you need to get pausing, then you can do that, especially if you need to get that graph. All right, moving on. This is going to be a comparison showing you the difference between when we run a reaction with and without an enzyme. So the first curve you're going to notice pop up in blue, and that's going to go from reactant to product without the enzyme. Notice how high we have to go in order to gain enough energy so that our reaction can run. What should happen when we add the enzyme? If you guessed it should lower, you got it right. In theory, we should have a lowering of the activation energy. So here you'll notice we've labeled it free energy activation. We've kind of freed up some energy, and it makes things easier. So the progress of our reaction goes faster. Notice we end up with the same products. The products are not changed by the presence of an enzyme. It simply makes it easier for us to get to those products. We require less energy for the reaction to occur. Okay, so graphically it would look